Why do soap bubbles show shifting rainbow colors? Why does a laser stay sharp while a flashlight spreads out? And how can two beams of light combine to become brighter or disappear completely? All of this happens when light stops behaving like straight rays and starts acting like a wave. Try this. Take a small sheet of paper and poke two tiny holes close together. Shine a laser through them onto a wall. Instead of two bright spots, you'll see a whole pattern of bright and dark stripes. This pattern appears because light waves add up and cancel out. And now we're stepping into the first big idea: interference. When two waves meet, they don't ignore each other. They combine. If a peak meets another peak, the light becomes brighter. If a peak meets a dip, they cancel and create darkness. That's why thin layers like soap bubbles and oil films glow with colorful patterns. The reflected waves interfere with each other, building and canceling in different colors. Now let's move into something just as fascinating: diffraction. Even though light travels in straight lines, it bends and spreads when it passes through tiny openings or around edges. Make the opening smaller, and the spreading becomes bigger. This is why lasers, even though they look perfectly narrow, slowly widen as they travel. Every microscope, camera, and telescope is limited by diffraction. You can only focus light so sharply before it begins to spread. And now we come to one more powerful idea: polarization. Light waves normally vibrate in all directions, but certain filters allow only one direction to pass. This is why polarized sunglasses cut glare from road surfaces and water. They block one direction of vibration while letting the useful light through. This same trick makes LCD screens work, helps cameras reduce reflections, and even allows 3D movies to create separate images for each eye. Interference explains how waves combine, diffraction explains how waves spread, and polarization explains how waves can be filtered and controlled. Together, these three behaviors are the backbone of modern optical technology. Lasers rely on interference to stay pure and sharp. Fiber optics guide light by minimizing diffraction. Holograms are nothing but captured interference patterns. Microscopes and telescopes push against diffraction limits to sharpen images. And screens, sunglasses, and cameras use polarization to shape the light we see. Wave optics doesn't replace ray optics, it completes it. Ray optics tells us where light travels. Wave optics tells us why light behaves the way it does. And here's the real curiosity to carry forward. If light can bend, spread, cancel, strengthen, vibrate, and interfere like a wave, what happens when it interacts with atoms themselves? That question takes us straight into modern physics.